4 hours ago, the threat models inside NASA turned red, and for the first time in years, the alerts were not theoretical. It is February 22nd, 2026, and what I am about to explain is not a simulation, not a drill, and not a distant possibility. As we speak, 3I Atlas, the object astronomers have tracked for the last 18 months, has experienced what officials are calling a catastrophic disruption event. That is the technical phrase. In plain language, it has released something, and that something is now moving through space with structure and intent. At 8:14 UTC, Deep Space Radar confirmed that a debris cloud separated from the main body. This was not ordinary dust, and it was not vaporized ice. Radar resolved roughly 50,000 individual solid fragments, each about the size of a river pebble, traveling together in a tight, coherent formation. Normally, when a comet breaks apart, fragments scatter randomly, like shattered glass spreading across concrete. The pieces drift apart chaotically, pulled by gravity and solar radiation. But the data coming in from the James Webb Space Telescope shows something entirely different. These fragments are not dispersing. They are clustering into a dense ribbon-like stream with an angle of dispersion of less than 0.02 degrees. That level of precision is extraordinary. Nature favors disorder. Entropy ensures randomness. Yet what we are observing looks less like an explosion and more like a controlled release. The shape of the cloud is concerning, but the real issue is its path. Using orbital parameters published this morning by the Minor Planet Center, trajectory models show that within 48 hours, this stream does not miss Earth. It intersects our orbital plane directly. For decades, planetary defense planning focused on single large impactors, the kind that ended the age of dinosaurs, but physics tells us that 50,000 high-velocity fragments create a far more complex problem. Instead of one object to track, we now face a shotgun blast of hypervelocity projectiles aimed at the region where our satellites operate. European Space Agency has activated emergency debris protocols. NASA has classified the situation as a Level 1 critical event. More troubling still, velocity measurements indicate the fragments are accelerating. They are not slowing due to solar pressure as expected. They are gaining speed. That single detail forces a reevaluation of everything we thought we understood about 3I Atlas. It is no longer just a passing interstellar visitor. It has left something behind, and that something is moving with purpose. To understand how quickly this unfolded, we need to look at the last 12 hours. Until early this morning, 3I Atlas was simply another hyperbolic object discovered in late 2024. Its high inclination made it interesting, but its behavior matched that of a typical cometary body. It appeared to be nothing more than ice and rock tumbling through vacuum. That assumption changed at 4 UTC when the first anomaly appeared, not through optical observation, but from a routine radar pinged by the Deep Space Network's Goldstone antenna in California. Engineers expected a single clean return signal representing the comet's nucleus. Instead, they saw fractured echoes, thousands of tiny reflections clustered around the main body. At first, technicians suspected equipment malfunction or atmospheric interference. In radio astronomy, noise often means failure, but this pattern was structured and rhythmic. Within 20 minutes, NASA initiated an emergency retasking of the James Webb Space Telescope. By 5:30 UTC, the telescope locked onto the coordinates and began imaging in near-infrared. The images confirmed what radar hinted at. The comet had not merely broken apart, it had released a swarm, and that realization marked the beginning of a very different conversation. But in science, One instrument is never enough. A single data source can mislead. Two can be coincidence. Three, establish fact. And within the next hour, 3 independent observatories confirmed what no one wanted to believe. While Goldstone radar tracked the density of the cloud, the Gaia spacecraft independently recorded a sudden brightness flare of magnitude 4.2 at the exact same coordinates. At nearly the same time, the Vera C. Rubin Observatory in Chile cross-referenced the event using its wide-field survey camera, radar, astrometry, and optical imaging, 3 separate methodologies, one identical conclusion. This was not a sensor glitch. It was real. And what they found was not a debris field in the normal sense. When a comet disintegrates due to tidal forces or thermal stress, the pieces follow a power law distribution. You get mountain-sized chunks, medium fragments, and clouds of dust. Look at Shoemaker-Levy, 9 inches, 1,994. Its fragments varied wildly in size before impacting Jupiter. Nature does not sort broken objects neatly, yet preliminary analysis from teams at Harvard and Caltech indicates that roughly 90% of these 50,000 fragments are uniform. Spectral readings place them between 4 and 6 centimeters in diameter, with size variation of less than 3 millimeters. That level of uniformity does not happen by accident. If you shatter a rock, you do not get 50,000 near-identical spheres. You get dust and jagged shards. That was anomaly number 1. Uniformity. Then came anomaly number 2. At 7:45 UTC, as sunrise approached over the Atlantic, the European debris tracking teams noticed something even stranger. Instead of trailing behind the comet like a typical meteor stream, these fragments were ahead of it. They had been ejected forward. In physics, pushing mass forward requires energy. If debris shoots out in the direction of travel, the parent body should recoil or slow down. There should be a clear transfer of momentum. Yet telemetry showed no measurable deceleration in the main body of 3I Atlas. Infrared data from the James Webb Telescope revealed no major heat spike, no explosive jet of outgassing that could account for such acceleration. The comet remained cold, so we are left with a cold object releasing 50,000 nearly identical spheres and pushing them forward without visible propulsion. That should not be possible under classical mechanics. Then anomaly number 3 emerged, density. Meteor showers like the Perseids or Leonids can produce thousands of meteors per hour under ideal conditions. That is considered intense. Based on radar cross-section data, this new stream is roughly 400 times denser than the Leonids. Imagine a hailstorm in which each stone is iron or rock traveling at 42 kilometers per second. That is the scale of what is approaching. And just when astronomers thought the event could still be modeled as a bizarre but natural disruption, the Doppler data changed. At 9 UTC, frequency shifts began to fluctuate. The fragments were not simply moving forward, they were oscillating. The radar signature showed a synchronized vibration pattern. Rock does not oscillate in unison unless acted upon by an external force. Was it the solar wind, a magnetic interaction, or something else entirely? To answer that question, radio astronomers turned to the Green Bank Telescope in West Virginia. At 11:15 UTC, its ultra-sensitive receivers isolated the oscillation frequency. The fragments were not vibrating randomly. They were oscillating coherently at exactly 440 Hz. 50,000 separate objects spaced across hundreds of kilometers, moving in synchrony at a single frequency. In nature, synchronization on this scale is almost unheard of. Fireflies sometimes flash together. Crickets may chirp in patterns, but inert rock does not hum in perfect unison. If you drop a box of tuning forks, they ring differently and fade independently. These fragments began vibrating simultaneously and have not stopped. And that realization forced physicists to confront something far more unsettling than a simple comet breakup. It forced them to question whether we were still observing geology at all. Once the 440 Hz oscillation was confirmed by the Green Bank telescope, the conversation shifted from unusual to unprecedented. In classical mechanics, a rock is passive matter. It has mass, velocity, and responds to gravity. That is all. If you throw a stone through empty space, it follows a straight path unless acted upon by a force. It does not vibrate with measurable coherence. Yet these 50,000 fragments were not only vibrating, they were doing so in perfect synchrony. The first hypothesis was solar-wind interaction. The sun constantly emits charged particles that can influence small bodies. But when physicists calculated the force required to produce a 440 Hz oscillation in a 4-centimeter object made of rock or iron, the numbers did not work. The solar wind would be like a light breeze pushing against a freight train. The fragments would need to be extremely light, almost hollow, to respond that dramatically. And that possibility opened an unsettling line of thought. If they are hollow, they are not solid pebbles. They are shells. Then came the second impossibility, conservation of momentum. Earlier, we established that the fragments were ejected forward. According to Newton's third law, every action produces an equal and opposite reaction. If a comet pushes mass forward, it must slow down. Momentum must be conserved. Yet telemetry from the main body of 3I Atlas showed no measurable recoil. Its velocity remained constant within 0.001%. It released 50,000 fragments at high speed without losing momentum. In a closed system, that cannot happen unless the system is not closed. At 1340 UTC, a preliminary memo from researchers associated with the Galileo project suggested that the non-gravitational acceleration observed was consistent with propulsion. That word is not used lightly in astrophysics. Propulsion implies internal energy. It implies a mechanism. It implies intent. The statistical odds compounded the concern. The probability of uniform fragmentation at that scale is extraordinarily small. The probability of coherent oscillation is even smaller. The probability of zero recoil during forward ejection is effectively zero, yet all three conditions occurred together in a single event. Then, at 14 UTC, the issue moved beyond physics and into global security. The European Space Agency Space Debris Office in Darmstadt fed the updated trajectory data into its collision avoidance software, the same system that protects the International Space Station. The model failed, not because of volume, but because the fragments were not following Kepler's laws of orbital motion. Objects in orbit accelerate as they approach the Sun and slow as they move away. They follow predictable curves, but over the previous 2 hours, the stream's curvature had begun to flatten. The fragments were resisting gravitational pull. Imagine throwing a baseball and watching it suddenly ignore gravity mid-flight, continuing in a straight line. That requires continuous force. That requires guidance. At 1430 UTC, NASA abruptly cut the public radar feed from Goldstone. No explanation was given. At the same time, the Deep Space Network redirected its largest antennas in Madrid and Canberra to focus exclusively on the stream. They were no longer simply tracking it, they were listening. Because if you have coherent oscillation, non-gravitational acceleration, and resistance to orbital curvature, you are no longer dealing with a simple rock formation. You are dealing with something that behaves like technology. The implications are profound. If natural, this event would demand a rewrite of modern physics. If artificial, then 3I Atlas is not a comet. It is a carrier. And just as that possibility began circulating quietly among researchers, a leak from an observatory in Chile revealed what forced NASA to shut down the feed. The oscillation was not just a hum, it contained structure, and that structure changed everything. Everything documented by 14 UTC uniform fragments, coherent vibration, non-gravitational acceleration was already extraordinary. But at 1515 UTC, the situation escalated again. The Atacama Large Millimeter Array, known as ALMA, detected something entirely new. ALMA is designed to observe the cold universe. It studies faint emissions from dust and distant galaxies. It does not typically register sharp, coherent microwave bursts from nearby debris clouds. Yet its band 6 receivers were suddenly saturated by signals originating from within the fragment stream itself. The fragments were not only vibrating, they were transmitting. ALMA recorded rapid microwave pulses lasting just 3 milliseconds each, jumping from fragment to fragment at light speed. The pattern resembled a neural network firing. It resembled coordinated data exchange. This was not random electromagnetic noise. Analysis of the pulse structure revealed distinct modulation patterns. More striking still, embedded within the sequence were prime numbers 2, 3, 5, 7, 11, encoded within pulse intervals. Prime sequences are mathematically significant because they do not arise easily from chaotic processes. They require deliberate structure. To coordinate 50,000 objects across thousands of kilometers with millisecond precision requires a shared clock. It requires synchronization. It requires processing power. And the moment ALMA detected the activation of this microwave network, the entire stream shifted trajectory by 0.04 degrees. The adjustment was simultaneous. It was not scattering or drifting. It was a coordinated course correction aimed directly toward Earth's position 48 hours ahead. If this were a natural breakup, debris would continue along the parent comet's orbit. Instead, this swarm recalculated for Earth's motion and corrected to ensure interception. That realization explains why NASA cut the Goldstone feed. It explains why the European Space Agency elevated the Planetary Defense Alert to Level 4, something never before declared. We are no longer discussing a meteor shower. We are observing a deployed system that activated, checked its coordinates, and adjusted course. And the targeting is specific. Updated trajectory models show the stream is not aimed at the oceans or lower atmosphere. It is targeting the northern hemisphere's high-latitude orbital belt, the region where communication satellites operate. That includes weather monitoring, GPS systems, financial networks, and defense infrastructure. Let us separate certainty from speculation. Fact 1. 3. Atlas released 50,000 uniform fragments. Fact 2. They oscillate coherently at 440 Hz. Fact 3. They executed a powered course correction. Fact 4. They are converging on Earth's orbital infrastructure. These are confirmed observations from NASA, ESA, and ALMA within the past 6 hours. Now consider distance and time. The swarm is currently 1.2 million kilometers away. Each hour reduces that gap by roughly 150,000 kilometers. In 48 hours, on February 24th, it will intersect Earth's orbital plane. Right now, telescopes remain locked. Military tracking systems are active. Data streams are monitored continuously. The swarm is inbound, closing steadily, its formation intact. And as the fragments draw nearer, the central question becomes unavoidable. If 3I Atlas functioned as a delivery vehicle, and these fragments represent its payload, What happens when they reach the satellites they appear to be targeting? If the targeting is intentional, then the objective is not landfall. It is disruption. The northern hemisphere's high-latitude orbital belt is not random space. It is where critical communications satellites, cluster navigation arrays, military relays, broadband networks, weather systems, and financial timing infrastructure remove or damage that layer, and modern civilization does not collapse instantly, but it fractures. GPS errors ripple through aviation, banking timestamps fail, emergency communications degrade. This is not cinematic destruction, it is systemic interference. By 16 UTC, analysts inside NASA and the European Space Agency were running collision simulations under extreme assumptions. If even a fraction of the 50,000 fragments maintain structural integrity at 42 kilometers per second, the kinetic energy released in orbital altitude would rival large anti-satellite tests but multiplied thousands of times. The difference is scale and simultaneity. A single impact can be managed. A distributed impact across a belt of satellites creates cascading debris. That cascade could render entire orbital lanes unusable for years. Yet, the more they modeled, the less the fragments behaved like uncontrolled projectiles. The synchronized 440 Hz oscillation remained stable. The microwave pulse network, first detected by the Atacama Large Millimeter Array, continued in bursts. Prime intervals repeated. Transmission hops moved across the formation in patterns that resembled load balancing in digital networks. This was not random chatter. It looked like coordination. Military observers were brought into the loop quietly, not because there was evidence of hostile origin, but because the behavior crossed from astronomical anomaly into aerospace relevance. If the fragments were hollow shells, as mass-to-area ratio suggested, they could be engineered for maximum cross-sectional interaction designed to graze, scrape, or disable without fully vaporizing. That is speculation, but it is grounded in measurable data, low density, high coherence, controlled trajectory. Meanwhile, a new detail emerged from Doppler refinement. The oscillation amplitude was not constant. It modulated slightly when the stream adjusted orientation relative to Earth's magnetosphere. That suggests responsiveness. Natural rock does not respond to planetary magnetic gradients with synchronized frequency tuning. If anything, it tumbles unpredictably. These fragments corrected orientation subtly, as if aligning. At 1820 UTC, tracking updates indicated another micro-adjustment, only 0.01 degrees, but again simultaneous across the formation. The correction compensated for Earth's rotation and the drift of target satellites. That implies predictive modeling internal to the swarm. Whether that modeling is autonomous or centrally directed remains unknown. But it is adaptive. Officials avoided public statements beyond confirming an active debris assessment. That phrasing understates the complexity. We are not facing a single collision window. We are facing a dynamic system approaching infrastructure that underpins daily life. Power grids depend on synchronized timing. Aircraft rely on satellite positioning. Shipping lanes, emergency services, even internet backbone routing depend indirectly on orbital assets. And yet, amid the concern, one possibility remains. If this is natural, if some unknown physical process can create uniform fragmentation, coherent oscillation, microwave signaling, and controlled trajectory, then we stand at the edge of a scientific revolution. It would imply new electromagnetic coupling mechanisms, new states of matter, perhaps interactions not yet described by existing theory. That outcome would rewrite textbooks, not battle plans. But time does not pause for theory. The swarm continues closing the distance. As of the latest update, it is under 1 million kilometers away. Velocity remains steady. Oscillation remains synchronized. The microwave network remains active. The world watches quietly. Analysts update models hourly. Satellites adjust minor orbits where possible, but fuel constraints limit maneuver windows. In 48 hours from the initial alert, interception becomes possible. And as that clock counts down, the distinction between discovery and defense grows thinner. By the time you hear this, the swarm will be significantly closer. Distance in space shrinks quickly at hypervelocity. What was once an abstract object at astronomical scale is now a measurable, approaching system. The latest consolidated tracking places the fragments at approximately 800,000 kilometers and closing. At their current speed, orbital intersection remains projected for February 24th. Inside control rooms, the focus has shifted from classification to mitigation. Satellite operators are evaluating last-minute repositioning burns. Some craft can shift altitude by a few kilometers. Others lack sufficient propellant. The difficulty lies not in predicting a single impact point, but in predicting 50,000 micro-trajectories that continue adjusting in formation. The 440 Hz oscillation persists. Independent confirmation from the Green Bank telescope shows phase stability across the entire stream. That stability suggests a shared timing source. Whether distributed or centralized is unknown. What is known is that the microwave pulses recorded by ALMA continue to propagate in prime number sequences. The syntax has not degraded. If anything, signal clarity has improved as the swarm approaches. One scenario under quiet review is that the fragments are not weapons, but probes units designed to sample electromagnetic environments. The northern orbital belt is dense with radio transmissions, radar sweeps, and encrypted communications. From a purely observational standpoint, it is a rich data field. A swarm passing through that region could harvest immense information in minutes. That possibility does not reduce risk. A dense field of maneuvering shells moving through satellite clusters remains hazardous regardless of intent. Another scenario considers fragmentation upon entry. If the units disperse further when encountering Earth's magnetosphere, they could create artificial meteor activity at high altitude, ionizing atmospheric layers and disrupting radio frequencies. Such an event would resemble a severe solar storm in effect, though not in origin. Yet, unlike solar flares, this system appears directed. The uncomfortable reality is that we do not yet know which explanation is correct. Natural anomaly, autonomous probe array, or something else entirely, each carries different consequences. But uncertainty does not erase observable facts. The fragments are uniform. They vibrate coherently. They maneuver collectively. They communicate. In the coming hours, we will learn more. As the swarm enters stronger gravitational influence, its response will clarify much. If curvature increases naturally, the propulsion hypothesis weakens. If straight-line resistance continues, artificial control gains weight. Physics will reveal the truth, even if quietly. For now, global infrastructure stands alert but steady. No satellite failures have occurred yet. No impacts have been recorded. The swarm remains inbound, formation intact, microwave pulses repeating in measured cadence. And that brings us to the defining point. Humanity has always looked outward expecting randomness, asteroids, comets, natural chaos. What we are observing challenges that expectation, whether it proves to be a breakthrough in physics or the first confirmed instance of engineered interstellar technology. History will mark these 48 hours as pivotal. We are about to find out what 3I Atlas truly is, not by speculation, but by outcome. When the swarm intersects our orbital belt, the data will speak. Either gravity reasserts control, or guidance continues. Either the fragments disperse harmlessly, or they execute a mission. Until that moment, telescopes remain locked, tracking arrays active, analysts vigilant. The clock continues counting down. Stay informed, stay critical, and follow this channel for verified updates as this unprecedented event unfolds. The next 48 hours may redefine everything we think we know about the universe and our place within it.